All right, hello everyone. I'm Zixia, a PhD student from University of Virginia. Professor Fong is also from University of Virginia. I'm focused on AFO science, and she's more focused on wildfire science. Professor Liu is from PNNL. He's very good at climate modeling. So the work we are going to present is FireDataForge. So in short, it is a tool that helps to download wildfire data from multiple sources and then integrate them into a union shape. We hope this work can help with users that have minimum knowledge with wildfire science and geographic information systems. So first, what makes a fire? So basically there are three factors that cause fire: heat, the oxygen, the fuel. So this is like what people care about and what kind of data we are going to retrieve. So basically from the heat side, we care about the fire behavior and the terrain. For the oxygen, it's basically the weather. The fuel, it's basically the vegetation and the building environment. So there's a huge gap here because actually each sources, they kind of disagree. So for the weather, we have a hourly data, so it's very dense in the time resolution, but it only has 3 kilometers. So basically people there, they simulate in the scale of the whole Earth. And for the fire observation, we have some satellite observations. So we get it every 12 hours. So it's basically because the satellite orbits the Earth every 12 hours. And we have the 300 meters of spatial resolution. And also we have this kind of satellite image, these elevations, so they are static. Those buildings and bone histories. So all of them have different kind of resolutions. To be honest, they are provided by different agencies, by different research groups in different universities. So people with minimum knowledge how to deal with this kind of data. And for the existing works, so there's some kind of trade-off of the existing works. For example, on the one hand, access libraries. We have Google Earth Engine, some Herbie, some very famous packages. They are on demand, which means you can just give the coordinates and the time frame, so you get the data. And they are also configurable, so you have the package and you can do a lot of things. But they don't have a unified output, and also it's very difficult to get a list of all the coordinates and time frame if you just want a fire. I mean, you need to figure out what the exact data for it. And on the other hand, there's a lot of existing machine learning datasets. So basically, they compile the existing wildfire events into a static dataset, but they are not that dynamic. If you want some fire data that's happened after they compile that dataset, that's basically impossible. And they are fixed, which means it's very difficult for you to configure it in your in what kind of data shape you want. So our proposed architecture is based on the fire event ID. So multi-agencies have a MTBS event ID that basically gives each fire event a unique identifier. So our pipeline basically receives this kind of event ID. Then we find out the fire, we pull the different sources from different places in parallel, and then we reproject, resample, and align them on the same grid. So in the end, we will get one array with 20 layers, and they are all aligned with each other with their own metadata. So this is like the layers we have. Basically, we have fire behavior data, so some fire parameter describe what the fire looks like. And for the weather data, we have it's basically just the wind and the humidity. For the vegetation, we have the density and the type of vegetation at on the map. For the terrain, we have like the height. Basically, the fire tends to like burn upwards rather than downwards. For the building environment, we have some data that marks the building height of the area, so we know if this it is an urban area or if it is a rural area. For the imaging, it's basically just to give an idea of what kind of the area it is. So regarding our core idea, we do the resampling just follows the nature of the data type, so which means we will not invent any details that's not from the source dataset. For example, for the category, we use the nearest one, so we're not introducing new categories or something. For the continuous dataset, like the wind elevation, we use bilinear to resample it. And for those building heights, they are very tricky because they are actually shapes. So we use some error-weighted algorithm to get a bitmap that shows the basically averaged building height in each region. And for the our clock design, so because we can keep the metadata of each time frame. So actually, like in the downstream tasks like simulator, we can set up a simulator clock, and we just keep up the most recent time frame from our dataset. So the whole dataset can rows, and it does not take a lot of memory usage or disk spaces. In our implementation, we build it in a way that these APIs can be used as plugins. So all those kind of different sources, like the NASA, Google Earth Engine, although they from different sources and are in different shapes, we can use the common API to fetch, reproject resample, and then put it into a metadata. So just for some virtualization, this is the native reads. We can see they all have different data types and they have different resolutions. And after we unified them, we then put it into a common grid. So the downstream users, like the machine learning algorithm developer and also the educators, they can use this kind of data set better, so they don't need to like manually do all the pipeline stuff. So that's basically our work. We believe for some takeouts, we believe we have lowered the data barrier, so the Wildfire data sets can be accessible to broader users. So what we did is we have implemented the automatic retrieval and harmonization. And the output we have is a very generic NumPy array with metadata in it. And also the model, and also the implementation is modular and scalable. So we have our GitHub and also our preprint version there. So I think that's all I want to share. And any questions?
Thank you. We can only afford one question from the audience.
So, how useful do you think this would be in predicting where the wildfires might be, like a weather forecast?
Yeah, so actually we already have some work on the wildfire simulator, but those models are most built by scientists in the fire department, and they are not having enough input from the machine learning community. But like on the other side, machine learning communities, they don't have a lot of updated data sets, and they can only like use some very outdated one. And if like there's a new event, they have no ideas of like how to like even get these kind of data sets.
Well, like I said, if you use an ensemble method with smaller members of a larger ensemble, you can update the ensemble without having to train the whole thing. So if there's new data, you don't have to retrain everything else.
Yeah, that's also like very useful if we have like trends data on some time frame of the on the old data set, and if we get like new fires like the recent ones, we can use the new fires to verify and keep improving the model. So that's also, I think, very useful for downstream tasks like some ensembling and resembling predictors.
All right, thank you.
Okay.
Okay, our next presentation.